Now that we know how to write equilibrium constant expressions, we can plug in the values for each of the concentrations. So remember, when you have those brackets, that is molarity. You can only put in values if they are at equilibrium. So your problem should say something like at equilibrium. So let's go ahead and do this problem. We do have our values at equilibrium, and it wants us to find the equilibrium constant. So I'm going to first write my formula. So remember, it's products over reactants. So look to the right-hand side. There's my products. So your coefficients become exponents, and there's my reactants. And I have my values right here. So let's go ahead and plug each of those in. And when I do my math, I end up getting a 0.2 as a value. So remember, your equilibrium constant should have no units. So it should just be a number. And recall that if it is a number less than 1, that means I'm going to have more reactants. And if it's a number greater than 1, I will have more products. And this one is less than 1, so I'm going to end up having more reactants at equilibrium. So the big take-home message is make sure it says at equilibrium. So if it's at equilibrium, you can put it into your formula. If it's not, you have to take an extra step. All right, let's look at another problem. This one, we're given the equilibrium constant, and we just need to find one of the molarity values. So the first step is to always write an equation. Don't skip this step. Even if you think you can do it in your head, always write your equilibrium constant expression. So recall KEQ just means a general equilibrium, but treat it like a KC is most of the time is how I've seen it. And you would know that it's a KC because all our values that we're plugging in are molarity values. All right, so we have KEQ, and again, products over reactants. So we're going to multiply those two together. And then our reactants, again, multiply these. And then let's plug in what we know. So I'm going to cross multiply. And so I'm going to end up getting c squared on this side times 1 will just be c squared. And then on this other side, I'll get 12 times 3 times 2 squared, which would be 4. So I end up with 12 times 12, which is 144. And then to get rid of that squared, I'm going to take the square root of each side. So I get c is equal to 12. So this is a common thing where you will end up with a square and you'll have to take the square root to get the answer. And notice that at the beginning, it says all these values are at equilibrium. All right, let's do a pressure example just so that you can compare those. So we are going to find the Kp. Start with writing the formula. So remember, we're given pressure, so we're going to use parentheses, but all the rules apply. And it should tell us that these are equilibrium values, and it doesn't, but we're going to assume that they are. So I need to fix this slide. So let's put in each of the values here. So we have 0.4. So we're going to solve for this NO2. My Kp is going to be 158. So I end up with 158 is equal to, and I'm going to cross multiply. You can just do your algebra however you feel comfortable doing it. And I'm going to divide each side by 158. So when I do the math, I end up with 347, and this is a pressure. So I should have my pressure unit, which is atmospheres. All right, so just an example with pressure. All right, let's look at an example if our values are not at equilibrium. If we're not at equilibrium, we need to use what's called an ice chart. So you're going to have your equation that's all balanced, and I'm going to put that across the top. And I like to separate my reactants from my products just so I can keep them straight. And so that's what goes across the top. And then what goes down the left-hand side is ice. So ice stands for initial change equilibrium. So in this case, I've written it all out so you can see it, but I would just write an I, a C, and an E. And then we're going to plug into this grid. So you're just going to match up what's what. So let's look at our values. So we have at the beginning, A is 1.3, or excuse me, 1.2. B is 1.2. And what else do we know? It says at equilibrium. So that means I need to be at this equilibrium line. It says C is 0.8. And find our equilibrium constant. All right, so from that beginning, I can fill in the rest of this chart. So let's start with our initial values. So in our initial values, I have A and B. And when I fill the container with these gases, I'm not going to have any C and D. So if it doesn't tell you what it is, you're going to assume that you're starting with nothing. For the change, I'm going to look at the stoichiometry, and I first need to determine which way it's going to go. Now, this one is kind of simple because I only have reactants, so I know that overall I'm going to make products. So I'm going to have a shift towards the product side. And it might not shift all the way because it's equilibrium, but it's going to shift a little bit towards the product side. So how I do the change is I'm going to look at the stoichiometry, and the stoichiometry is 1 to 1 to 1 to 2. And so that's what I'm going to put into my change. So my reactants are going to become products. So they're going to go away by 1x or just x. And my products are going to appear in this with the stoichiometry. So this one is going to appear by 1x, and this one is going to appear by 2x. So again, you have the stoichiometry in that change line. From this point, I need to figure out what x is, and I happen to have one complete column filled in. Well, I can do a little math problem with this, a little algebra problem, and I'm going to ask myself 0 plus x equals 0.8. So therefore, what does x equal? Well, x equals 0.8. So I can go through and substitute 0.8 every time I see an x. That one we already did. So subtracting 1.2 minus 0.8, I'm going to get 0.4 here. And this one's also going to be 0.4. And this one's going to be plus 1.6. It's the equilibrium values that go into the equation. I haven't written the equation yet. We could have done that first thing. Let's go ahead and write it. So Kc equals my products my products over my reactants. And again, you can only put equilibrium values into your equation. So you're not going to put your initial values, only your equilibrium values. So you use this ice chart and the stoichiometry to help you figure out what equilibrium values you should put in. So on the top, I have 0.8 and 1.6 squared, because that's what my equation says. And on the bottom, I have my 0.4 times 0.4. When I do the math, I get 12.8. So looking at that value, that tells me I'm going to have more products than reactants. And I can actually see that. Look at what the molarity values are. 0.8 and 1.6, that is more products than reactants. Okay, let's do another one. This one is with pressure. And it says find the Kp. So that's going to remind me to use parentheses. And I have beginning values and I have an equilibrium value. And you can see this line dividing the reactants from the products. And let's go ahead and fill in what we know. So it says at the beginning, the pressure of E is 5 atmospheres. So I'm just going to put 5 there. And it says at equilibrium, the pressure of G is 2. All right, so that's all that they give us. We should be able to plug everything in though. So at the beginning, it looks like I just have reactants. So this is kind of similar to the last problem. And I'm going to have no products, so put in my zeros. Then I'm going to look at the stoichiometry. So it is 2 to 1 to 2. So I know that I'm going to go this way because these guys are at 0. So I know that I'm going to make more products. So my products are going to up here in a ratio of 1 to 2. And I know that my reactants are going to disappear by 2. I can fill in one whole column right here that gives me all the values. So I'm going to do a little algebra problem. So 0 plus 2x equals 2. And solving for x, x equals 1. So I can go put a 1 where all the x's are and then figure out what the value is going to be. So on this first column, I'm going to have 5 minus 2, so I can get 3. And on this next one, I'm going to have 0 plus 1, so I'll get a 1. And then I know this last one is already a 2. It already gave me. The equilibrium values are the ones that you're going to plug into your equation. So let's write our Kp equation. So P for parentheses. So I'm going to have products over reactants. Whoops, let me do the P. Pf times the Pg squared divided by the Pe, which is also squared. So we'll go ahead and plug in our values. So F is 1, G is 2, and E is 3. So I end up with what? 4 divided by 9, which is also 0.44. So this is telling me that I am going to favor my reactants. So I should have more reactants at equilibrium. And you can look up your values and you can see that's true. You have a 3 molarity, or not molarity, we're in atmospheres. So we have 3 atmospheres on our reactant side, and on our product side, we have 1 atmosphere and 2 atmospheres. All right, let's talk about approximating. So we are using the stoichiometry to take away and to add, depending on which direction it's going. Sometimes when we go to do the problem, the only way to solve it is to use the quadratic equation. I have had AP readers tell me that there will never be a quadratic equation problem on the test. And I think it's because nobody really wants to grade it. It's going to be really difficult math. And on the AP test, they more want to test your chemistry knowledge than they do your math knowledge. So we are going to approximate. So when we have situations where we have to use the quadratic equation, we're going to drop this little minus x part, okay? So just like this says, 0.2 minus x, if x is very, very, very tiny, I'm just going to get 0.2 by the time I do sig figs. And let me show you a problem like this. So sometimes when we're doing our math, we are going to do some approximating. So let's look at this problem. So it says, in a study of halogen bond strength, 0.5 moles of iodine was heated in a 2.5 liter vessel, and the following reaction occurred. So I'm going to write my equation across the top. They're both gases, so they'll be in my equilibrium expression. And it says calculate the concentrations of iodine and just the I at equilibrium. And it gives us a temperature, but we don't really need that. But we do need this equilibrium constant, okay? So we are going to be solving for the reactants and the products, basically. It doesn't talk anything about being at equilibrium, so we have an initial concentration. And we even have to do math to find our initial concentration. So if I have 0.5 moles in a 2.5 liter vessel, Well, moles divided by liters would give me molarity. And so my molarity is going to be 0.2, and that would be the concentration of my I. That's the initial concentration. So we're going to do an ice chart. So my initial concentration of my iodine is going to be 0.2, and I don't have any of this. I'm going to have a change where I know that it's going to move towards the product side. So I'm going to have 0.2 minus X, and this one right here is going to be a plus 2X. And I don't have any equilibrium concentration. This is all I have. So I'm just going to bring everything down. So I'm going to have 0.2 minus X, and this is going to be 0 plus a 2X or just 2X. And then there's a line that separates my products from my reactants. I'm going to write my equilibrium constant expression. So I'm going to have, these are all molarity. So that one's going to be squared, and this one is going to be just by itself. And I'm going to plug in what I know. So I'm going to put in my Kc, which is given to me. It is 2.94 times 10 to the minus 10. Notice how small this is. So this X right here, this minus X, only a little tiny bit is going to be used to form products. And so this is what I mean by approximating. So we are going to drop that part. And let me just finish writing this out. So in order to solve for this, I'm going to have to use the quadratic equation. However, if I can eliminate this minus X, then it's going to make my math easier. And so that's what we're going to do here. So we're going to approximate, because this is just a tiny bit that's going to go over to the product side. And I know that because my reactants are going to be favored because my Kc is so small. So I can rewrite this equation and end up having 2.94 times 10 to the minus 10 equals 2x squared. So that would be 4x squared. Make sure you're doing your algebra correctly. And I'm just going to drop that minus x. I'm just going to have 0.2. So I'm going to cross multiply and divide by 4 and square root to get rid of that x squared. And I'm going to end up with x is equal to 3.83. So go ahead and stop the tape if you want to go through and do your math. I don't really have a lot of room to show you, but you are going to find out what x is. When you find out what x is, you need to take that and plug it into your equilibrium values. So I know that I, 2, is going to be this number. However, my just plain I, if you look up here at equilibrium, it says 2x. So I'm going to multiply that number times 2 because it's 2x. And I'm going to get 7.66 times 10 to the minus 6. And the problem wants both of those values. So it wants those equilibrium values. So here they are. So this is using that approximation rule. And again, you use it when our K is going to be so tiny so that I know which direction it goes. I guess if you started with products and we're going to reactants, and if you had a really large number, you would know that it wouldn't go backwards very much. So you could probably approximate it in that case also. One way around the approximations is to use square roots. So they will set up the problem so that you'll end up taking the square root to get rid of that minus x. So let's do one of those problems. So here we have H2 plus I2 and it's at equilibrium, and I get hydrogen iodide. And it says calculate all three equilibrium concentrations when initial concentrations are, and then it gives us the initial concentrations, and it also gives us the equilibrium constant. So let's start out with our ice chart, and then we'll write the equilibrium constant expression. So I'm just going to draw a line here and do my ice. On the AP test, writing an ice chart is showing your work. So sometimes they want to see the work. Well, you should always show your work, but this is a valid way to show your work. So we have initial concentrations. We have 0.2 here and 0.2 here. It's not told us anything else besides our equilibrium constant. And so I can fill this out as a 0. So I'm starting with no products and just reactants. So using the stoichiometry of a 1 to 1 to 2, I'm going to have the reaction go towards the products because, again, I don't have any products. So the equilibrium is going to shift that way. And this one will increase by 2x. I don't have any value at equilibrium, so I'm just going to bring them all down. So I have 0.2 minus x is this one, and this guy is 0.2 minus x. And then this one is just 2x. Let's write our equation. So we have Kc equals products over reactants. And then I can fill in what I know. And I do know what my Kc is. It's 64. And my Hi is 2x. And then each of the values down here is 0.x minus x. And I end up having both of them. You can write it like that, or you could write it out. All right. So if you look at this, I have everything. I'm going to go back to writing that as squared, just so you can see that I have squares all around. So this is a way to get rid of the minus x. So to avoid doing the quadratic formula. And so what I'm going to do is take the square root of everything. So I'm going to square root this, and I'll square root the top, and I'll square root the bottom here. So I'm going to square root of 64 would be 8. And then I'm going to have 2x here, and here I'm going to have 0.2 minus x. So this is just a way to get around the quadratic equation and not approximate. So just because you have a minus x doesn't mean you're always going to approximate. So sometimes you won't. So try to work out the problem, but then again, if it looks like you have to use the quadratic equation, then you would want to say in your explanation that minus x is really, really tiny. You couldn't, if you look at this k, that k is pretty large. And so you're not going to approximate this one because your k is so large. So this minus x is going to be pretty big. All right, let's go ahead and solve our problem. So I'm going to cross multiply. You do your math however you want to do this. So I have 8 times 0.2 minus x. And on this side, I have 2x. So let's distribute. Let's get our x's on the same side. So I'm going to add 8x to each side. And then divide by 10. And I have x is equal to 0.16. So looking at this x, to find the equilibrium concentrations, I need to take this x and stick it up here. So to find the H2 and the I2, I'm going to take 0.2 minus 0.16, and I'm going to get 0.040, and this is molar concentration. And then to get the HI equals 2x. So I'm going to do 2 times the 0.16, and I get that it's 0.32. Now you can check for correctness by taking each of these values and plugging it into your equation. So that means I would take this value, and I would take this value, and I put it into my original equation. And if you get that Kc is 64, then you know you've done it correctly. So that's just a way to check yourself to see if you got the right answer, is to go ahead and plug it into your equilibrium constant expression there. And we find that if you do that, you do get 64, so we've done it correctly. So equilibrium can go backwards too. So let's look at this example. So it says calculate the Kp for the following all gas reaction. And we have initial pressures. So the pressure of AB is 6. And then it gives us the equilibrium pressure concentration of element B as 2 atmospheres. So let's go ahead and fill out what we know. So I know that this is 6, it's atmospheres because we're doing pressure. And we know the equilibrium concentration of this one is 2. So because I'm starting out with 0 reactants, I know which direction this is going to go. It's going to be shifting this way. And this wants us to find the equilibrium constant for in pressure units. And so I need to do my change. So this is going to go away by a minus 2x. And this one is going to appear by a 2x and this one by a 1x or an x. Okay. So again, here's the dividing line between my products and my reactants. And because I'm starting with no reactants, it's going to shift that direction. So plan accordingly. I know that my products are going to disappear, my reactants are going to appear in this case until I reach equilibrium. Now I do have one column that's all solved in for me, so this makes our life easier. And so to figure this out, I'm going to go 2 plus 2x equals 2. So I know x is equal to 1. So I can just plug in that 1 every time I see the x. So on this one, I'm going to have 1 because 0 plus 1 is 1. And then I already know the b. And then the AB, I'm going to have 6 minus 2 times 1. So 6 minus 2 is going to be 4. So we do see that it shifts over towards that reactant side. I can probably guess that my pressure is going to be above 1 because it seems like my molarity on the products is still quite high. Let's see if that turns out to be the case. So my Kp, again, products over reactants. So if it's a P, I need to have parentheses, I need to have pressure. So the pressure of AB, and it's squared, and it's divided by the pressure of A2. Whoops, let me put the P in. And I multiply it by the pressure of B, and that one is squared. So let's go ahead and plug our numbers in. So I'm going to have 4 squared, and down here I'm going to have 1 times 2 squared. So I end up having 16 over 4, and I have my Kp equals 4. Remember your equilibrium constant numbers, they don't have a unit. So my answer is just 4, and that does confirm that I have more products than reactants.